So I will just give it a start today, and it will be short. And actually, I will not directly speak of drift ice, because first I will kind of connect what just Dirk said to the real world of Antarctic sea ice. So you've learned a lot on thermodynamics in somehow idealized configurations. But in practice, in my understanding, Antarctic sea ice is complicated, and more complicated than Arctic sea ice. It's more diverse, it's more of a mess. Arctic sea ice forms from the base and melts from the surface. That's basically what we know of it, whereas the Antarctic sea ice can grow by various means. It can grow from nucleation from the water column. It can grow, as in the Arctic, by congelation. It can also grow from the conversion of snow into ice because of flooding at the surface. And so that's a different system. And our understanding of it is, I would say, even less advanced than that of Arctic sea ice, because we have so few of these measurements. But in terms of differences, what I could take is just a model simulation, just to show. I discovered the mouse. It's a simulation. I wanted to illustrate that with field measurements, but I couldn't really find the best illustration of that from ice cores. So I figured I would take a simulation of mine, which I knew well, and I knew could make the point. And it's an illustration with histograms of the sea ice mass balance on an annual basis. So you count how many meters of ice form for each of the mechanisms that we know contribute to the sea ice mass balance. On the left, you have the Arctic, and you see what I was saying. You grow basically in the Arctic 1 meter of ice on average via the basal growth that Dirk described from Stefan's law, so congelation at the base, and you melt with roughly equal shares from the surface or from the bottom. In the Antarctic, you see the histograms do not look the same. First, you have more diverse growth mechanisms. You have basal growth, Stefan's law, but you also have a lot of growth in open water, because you have this divergent system that exposes open water to the atmosphere. And so you also grow a lot of ice from that. And if you look at an ice core, you would see you don't have this columnar ice structure, but you have instead randomly oriented crystals that make granular ice. And you also have this snow to ice conversion. It snows much more. The Arctic is a desert. The Antarctic is really a wet country. It snows a lot, and it snows so much that you can convert snow into ice by filling it with seawater. And it's efficient at large scale, and you can also detect that from ice cores. Regarding melting, you see that surface melting is very little, like Dirk just said. And most of the growth that you get is achieved via basal melt. Okay. Why don't we have surface melt in the Antarctic? I think it's an open question. I don't have the answer. I have an idea, but I think it could possibly be wrong. Do you know why, Dirk? No. So if anyone in the room wants to work on this problem, I think it's a good problem. It's linked with diurnal cycle, accumulation of humidity at the surface, maybe how the ice albedo feedback works, but I've never seen a convincing answer that I can tell. What I can tell is that basal melt is more efficient in the Antarctic, and I think this is because of the way sea ice melts in the Antarctic is really linked to the ice albedo feedback, as we call it. The Antarctic system is divergent, so you create a lot of open water, and you can trap solar radiation that way in the open water. And also another thing is that the ice thickness is not uniform, so you can easily lose the thinnest ice and create open water that way. And that's a very efficient means to trap solar radiation in the upper ocean. And as I told earlier, anytime you absorb solar radiation in the upper ocean, you would use that heat to melt the sea ice. And this is how basal melts comes into the game in the Antarctic. You have a lot of sun in spring because you are not that much to the South Pole. And you would trap that solar radiation in open water. And that creates this loop that we know for a certain amount of time is really efficient in the Southern Ocean, Antarctic sea ice. The loss of thin ice increases opening, so you increase open water, you increase solar absorption, and you increase basal melts. And that's more efficient than in the Arctic because the ice is generally thinner, and you also more towards the pole, and so you have more solar radiation. So that's one specificity of the Antarctic sea ice that I can partly explain, and you see we are in a research field. Another particularity of the Southern Ocean sea ice is that you have really strong interactions between the sea ice and the stratification below. And I think we are not fully able to describe things precisely, but in many papers already you have mention of these freezing entrainment feedbacks, and that dates back from works of Doug Martinson in the 1990s, reshuffled by Hugos recently over the last decade. And basically, in the Arctic you have a stratified ocean that doesn't respond much to any change in salt input. Whereas in the Southern Ocean, your subsurface ocean is weakly stratified. So any salinification would perturb the density and would lead to a redistribution of heat in the system. And so you have this freezing entrainment feedback that tells you that when you have ice growth, you salinify the surface ocean, and then you will deepen your mixed layer, entrain heat in the mixed layer, and that will reduce ice growth. So it's a negative feedback that limits the amount of basal growth in the Southern Ocean. So that's another specificity of the Antarctic system. And arguably, that these two processes, the ice albedo feedback and freezing entrainment feedback, explain somehow why you have this slow growth and rapid melting of the Antarctic sea ice. Okay. Another thing we can come back on in terms of differences between the Arctic and the Antarctic is that if you take ice cores and measure temperature and salinity inside the ice, you can find differences between both systems. And here you have salinity, mean salinity of the ice, and here you have temperature, mean temperature of the ice. And so you can see several things. We can take a bit of time to look at things. This is just recent work that one student in the lab is doing at the moment. She's compiled 1,000 ice cores and looked at the properties of the ice. And it's an histogram of all properties of the ice based on this compilation. And what you can see is really something that we cannot really explain very well yet. The Antarctic sea ice in red is generally more saline than the Arctic sea ice. And part of the answer is that Antarctic sea ice is younger and thinner, and so it has less time to lose the salt. But the other part is also linked to the input of salt linked to snow ice formation that we don't really well understand. So the Antarctic sea ice is more saline, probably because of the flooding of seawater, but we are not in a position to explain that as cleanly as for the Arctic. In terms of temperature, you also see that you have much more extreme cold temperatures for the Arctic. The warm regime is captured in both regions, but the cold regime from Arctic sea ice does not occur that much for Antarctic sea ice. Antarctic is warmer, so that's a surprise probably to some of you. I would argue that it's because of snow. So you have much more snow over Antarctic sea ice. It snows much more, and snow is a very good insulator. And so as it's a good insulator, you prevent the cold spells from the Antarctic continent to penetrate inside the ice. So that's also something that is not really standard in the understanding, but I think we have to progress to explain that. Yeah, I think check. I think I will stop here. It's 2 minutes left, and tomorrow we will know why and how sea ice moves. And okay, yeah, the first theory would be that one, but we hope we will develop things a bit further.